Welcome to The Explainer. Today we're going to tackle a really cool, kind of mind-bending idea, how two things that look completely different on the surface can actually be, secretly, the exact same thing. So let's kick things off with a little thought experiment. I want you to think about your favorite book, or maybe a movie you've seen 100 times. You know the characters, you know the plot, you know the whole structure inside and out. Now, what if you read that same book, but this time it's been translated into a completely different language? I mean, the words are all different, the sentences are put together in a new way, but the story is identical. The characters are the same, their relationships are the same, the plot unfolds in the exact same way. You're getting the same experience, just through a different lens. Well, in mathematics, there's a fantastic word for this very idea of structural sameness. It's called isomorphism. And it's all about looking past those surface-level details to find the identical blueprint hiding underneath. Think of an isomorphism as a kind of perfect translator, or maybe a decoder ring that connects two different mathematical groups. It's the proof that shows, hey, even though this group over here is made of numbers, and that one is made of, rotations of a triangle, they're actually playing by the exact same rulebook. Okay, so this is the formal definition from our source text. And yeah, I know, it looks pretty intense, a little intimidating, right? But don't worry. It's really just a very precise checklist for confirming that two things are structurally identical. We're going to unpack it piece by piece. So let's do that. Let's break it down. All that scary-looking text really just boils down to three key conditions. If you want to prove two groups are isomorphic, you need to find a function, or a mapping, that can tick all three of these boxes. First up, the mapping has to be one-to-one. That just means you can't have two different things in your starting group pointing to the same thing in your destination group. Everybody gets a unique partner. Second, it has to be onto. That means every single element in that destination group gets hit. Nobody is left out. But honestly, the third rule is where the real magic is. It has to preserve the operation. So this little formula here, this is the absolute heart of it all. It looks simple, but it's so powerful. What it's really saying is this. It doesn't matter if you combine two things in your first group and then use the map to see where the result goes. You'll get the exact same answer as if you map the two things over first and then combine them in the second group. And that, right there, is what we mean by preserving the structure. The way things interact, the results you get, the fundamental rules of the game, they're perfectly mirrored in both groups. The translation isn't just good, it's flawless. Okay, so our source text actually gives us a couple of extra notes that are super helpful for using this in the real world. Think of them as the fine print that actually makes everything easier to understand. For example, the source makes it clear that even though the formula looks like multiplication, this works for any kind of operation, like addition or anything else. And here's a big one. You don't have to check every single possible mapping between two groups. If you can find just one that ticks all three boxes, that's it. You're done. You've proven they're isomorphic. And this next note is a total lifesaver. Seriously, it's a super quick reality check. If you're working with finite groups, groups you can actually count, they have to have the exact same number of elements. If one has 5 elements and the other has 6, don't even bother with the other rules. There's no way they can be isomorphic. It's a fantastic first test. So that brings us to the big takeaway. We've gone through the checklist, we've looked at the rules, but why? Why does any of this matter? What's the real big idea here if two groups are isomorphic? I mean, what if we actually discovered if a mapping between two groups manages to jump through all of these hoops? It's not just that they're similar, we've found something way, way deeper. Our source gives us the answer, and it's a big one. It says that if two groups are isomorphic, they are, and I quote, abstractly identical. And that's not just a casual phrase, it's a huge mathematical statement. And this right here is the whole point. From the perspective of abstract algebra, mathematicians don't just see them as like each other, they literally see them as one and the same thing. They're just two different costumes for the exact same underlying structure. Anything you can prove about one of them is instantly and automatically true for the other. And that just leaves you with a really fascinating thought, doesn't it? If something as abstract as a mathematical group can have a secret identical twin hiding in plain sight, what else out there in our world, from the patterns in nature to the chord structures in music, is secretly just an isomorphism of something else? What else is just a different costume for the same fundamental idea?